Let's get started here. First of all, there's going to be a little bit of legacy in here, which it's unfortunate that it's legacy, as I'm sure a few friends in here will note.
Yes,
but
it's very unfortunate considering someone's actually invested in that place.
Yeah, but I'm going to
say we all.
Yeah. So it's going to hit the past as well as the future. Okay, one of the first things, if you know anything about data acquisition systems or have ever worked with them, it's complicated. This just gives you a little bit of an idea of the nest of wirings you get. And this is a small system. This is only the sensors for one engine early in its development. And I'm sure Jeff might recognize it, but this was the very, very first acquisition system that we put on the links when I actually had these little thermocouple amplifiers off on the side of the box. This was before I was able to develop my full system. And when you're doing data acquisition, there are a whole bunch of issues that you've got to deal with. The complexity means that tracing the circuits inside of your engine cowl gets really, really difficult. Interactions between systems, since you're on systems that can be inherently explosive, and I know one person here will cringe, but low voltage shorts can cause you some serious problems. Now, we had a lot of inherent safety in our system, so it wasn't quite at the risk in there, but you still don't want shorts and hot spots inside of a rocket engine. It's just not good. You get noise pickup, crosstalk, all sorts. I'm not going to read it because you're perfectly capable of reading the items I've got on the screen, but just to note that this is a very difficult thing to do. Now, the thing is that nature has known how to do this for a very long time. We've got 600 million years of continuous improvement in the nervous system of animals that are able to do interactions, like for example on a hand where there's a nerve ganglion there, it gets sensor signals back and does control effector outputs out from a local ganglia, passes the information on. If you touch a fire, your hand will jerk back long before the signal finishes getting passed up to there. I started looking at this back in my graduate school days when I was looking into, I was working on artificial intelligence and cognitive psychology under Dr. Herbert Simon at Carnegie Mellon. And I became very interested in some of the applications of this. So much so that when I got out of school and I got a job that had nothing to do with AI, I did some of it anyway. This is the final system from a company called CompuGuard in Pittsburgh, of which I was the designer. This is in 1981, and it was a hierarchical control and process control system. This thing is actually fielded. It went out to a number of sites, and I think somewhere, well, let's see, I don't see the names listed here. They may be later on. But the way this worked is very much like that human diagram. You've got analog and binary inputs down here at the bottom, and this is a tree structure. I only put some of the leaves. As you go up to these little units actually carried programs on them that could handle feedback control. The feedback control, so you would get an analog input that said something was over temperature, and this could locally take care of that problem. The program itself then became a pseudo input-output that you could read or write to from the next layer up, and so on up to the overall brain for an entire building complex. These went into some fairly large facilities. We were in Bethesda Medical Center, Vandenberg Air Force Base, some other places. And let's see, I've said most of that, but the takeaway on that sort of system is that since you've got to put programs on every single node, there is a scalability issue. an engineer has to actually get all of the specifications at each point in that tree and do something about it, and then prove that it does what it's got to do. And we weren't, well, there were some life safety issues on some things we do, and you can catch me over beers. I can tell you some of the interesting events that we had over the years. And anyone who has been in engineering around any high energy systems for some years has stories to tell. The output of this went into a paper. I was invited by Eric Drexler and by the Journal of British Interplanetary Society to put a paper in their issue in 1992. And as it turned out, they were so full on that one, the guy wanted to use my article as the main opening article on a second issue. So they did a 1994 issue. Now, once again, you're going to see the same theme here. We've got units that are the local reflex action handling the effectors and sensors in a tree going up. And at the top you have the humans, which I call the forebrain, where the actual actions happen. So the point is you try to do at each level as much as you can at that level, and only pass the things up if they require more information. Now, in the earlier CompuGuard's system, we had fail-safe and fail-soft. So if there was, let's say, a break in a link here, you could have a system set up so that it would either keep doing what it was doing, or that it could go into fall back into a special fail-safe state. Okay, and again, there's some of the information on it. One of the things that came out in my look at things for the BIS paper was that you need dynamic learning on some of those nodes. And at the time we were looking at it, 1994, the idea of doing dynamic learning, it was just too far out. Just the thought of trying to put that learning into a box such that your control outputs would not go out of bounds was a scary proposition. Now we get something that's a little bit familiar to folks out here who may actually, two people may have seen this diagram once long ago. On the linked space plane, and now as I said here, this is a very top level schematic diagram, and if I showed you any more I'd have to shred you. This is not an ITAR event, so this is as far as I'm willing to push it. But I have color-coded here the various networks, and by this point everything had gone over to Ethernet, so it was the way to transfer data around. We had boxes that acquired all of the data, the analog signals and so forth, and consolidated those and sent them onto another network where they could get stored in a central computer, which we called the ship's log. So you see here we basically had one of these data acquisition systems on each wing in the nose and in the engine area, and one in the cockpit area. There was a secondary network, which you see here, which was the black box system. And Immortal Data, now I did both of them, but sort of with different hats on. The basic data acquisition system I did as a consultant to XCOR and later as an employee. The data storage system here was a product of Immortal Data that we have a patent on. And the concept is that you also have these little boxes spread around the different places in the vehicle. So if we had a worse day, we would have a way of recovering the high rate data regardless of the fact that we were in pieces on the ground. This is a little bit from stuff that this is the linked spacecraft stuff. We had a box called the TARDIS, which Jeremy Voigt designed and came up with. This unit here was my sort of plug and play for sensors. I did the design on this. Jeremy came up with the idea for how to put a whole bunch of them together into one so that we can get hundreds and hundreds of analog points of control into this box. And you can see this is the box in place in the engine area. And down here is a gray box, which is actually the same gray box you saw in the opening slide, except with entirely different contents in it at this point. And it had ribbon cables coming in from here and from another place, and out of it came Ethernet, which went, in this case, out a connector, and I'll show you later how we did that in test. A lot of this, we had point-to-point wiring. We're still in those eras, and point-to-point is one of the easier ways to deal with a lot of this. In order to make it somewhat sane, we had a common sensor interface standard, which we laid out, and that allowed us on those little patch panels to do a plug and play no matter what the sensor type, because they all had the same interface presented to us, whether it was a thermocouple or whether it was a pressure transducer. We got an analog signal out of it that came in the same lines. We supplied some power to it as necessary, and we also had it set up that by that means we made sure that there was little problem on ground loops, because we starred our grounds out from the main power bus to point A and then up to point B. We never had any place where the grounds could tie into something earlier in the system. Now this shows you the real thing out on the hard stand. Now the thing to note, there's that little gray box I was talking about. The TARDIS is up in here. There are connectors that come off there, and those are the cables that we used. When we took it out to the field, we connected up on there, ran the cables into into the bunker, and then with everybody safe inside the bunker, we did the engine firings here. And this is a little bit of what it looks like. This is a hot flow day, and this is a cold flow day. And if I look here, this is my data acquisition control station, and I believe this is the data output that the person on the control box used. And that's where I displayed a low rate data of some of the numbers I was picking up through the system. And you can see some of it better here. This was Jeremy at his control station, and this is the numbers that are showing for him. And when this thing is running, he was getting live displays here, and if a number went red on there, he had this little button that he could hit, which usually shut the system down. Yes, I know at least one person chuckled.
How high a data flow rate are you talking about for these?
We were doing sample rates of 3,200 on 100 analog lines, and that was just on one engine on test. I had tested, you'll see later, I've tested it.
So like 3,200 data points per second?
Yeah, well, 3,200 data points per second per analog. And due to some things that made it simpler, we also were sampling the digital inputs at the same rate, because this was a rapid development, and I didn't have time to do things in a really sophisticated manner, so it was easier to just sample everything the same rate. And some of the keys, the way that things were done, and Jeff back there is the man who set up many of these ideas, is, X-Corp, we work very closely, and the philosophy at X-Corp was there was no dedicated test stand crew. There was no test stand out in the field that was owned by a group of engineers who had a proprietary control over it and told the propulsion people what they could do and not do. So the engine team owned that stand. Another thing was is that all the systems that were on there, mine included, were flight systems. So we weren't testing anything out there that was just throwaway for that. We were, everything was development. So all the gear of mine that you saw on there was being tested for flight. And it had to be done such a way that it was a very small team that was able to do the setup. And as you could see, that was basically in that prior slide was the size of the team that went out there for a hot fire test. And that entire team could, we got very good at it. We could have the thing set up in about 45 minutes to an hour and then start doing checks. Except when a certain piece of metal hardware would not go into place in the proper way. The reliability of our gear was very important. I earlier in this development effort had problems with a vendor software, which was one of the reasons why I ended up dusting off some of my old IDI system. Test days cost a lot of money. And if you get out there and you don't get the data, life is miserable for the guy who's supposed to get the data. Believe me, I know.
Does that mean there was a day that you didn't get the data?
Yeah, well, I do not want to name the vendor software that we were taking that liked to drop a packet at random, not just a packet, it would, let's put it this way, people who designed that particular software had no conception of real-time software in a system. And
however, once that was eliminated from the system, it was pretty
yeah.
I can answer that question tangentially. The data guy didn't get what he wanted, but the safety guy did. I was happy. They all came back.
Okay, moving on here. Now, we also, I used the same exact system with another, some other stuff that we did. We did aerodynamic testing using what we called the Trunnel. It was it started its life off as an F-150 truck and got really chopped and done in interesting ways so that we could carry parts of the aerodynamics on the vehicle.
That is the coolest F-150 I've ever seen.
And we had it out on the runway doing 120, I think. Now, this inside this plastic case, which is back on the back here, is another one of those patch panels. So all the sensors load that we had on there, I patched back into one of those panels. This is the data acquisition box, and that's the ribbon cable that goes off to the computer that stores it. And then we have the thing run up, and this is a mini example of the panels which were in the regular test days. Something also very similar to this was used in other situations. We used it not just for those aerodynamic tests, but also on the gear impact test. They borrowed our stuff and used some of it. And a key thing was the way that the people operated inside of that truck were very, very much like what the right seater in a flight test would do. And one of the things that was an interesting day for me was when we had our meeting looking at what was criticality 1, and I found that of the electronics, I was the only one who had something that was listed as criticality 1. And I had thought I managed to duck out on being that guy. And we sort of, what the issue was is that with the flutter data that you get on the laptop with the flight test engineer, he is taking straight analog data. They don't even want to see a Fourier transform, because the Fourier transform takes too long. And it's going to bin things, so by the time you see it, time has passed and you're dead. So, and that's the whole point, that he has to see this and he has to tell the pilot, stop. And that they have to be set for that. Now this only happens during a couple of early flights, but it's really key that it happens very quickly and that it's very reliable. And the decision was made that If for some reason my data systems were not functioning, it was basically the test day was over. They had to come back and work. They could not fly one of those tests without that system working. There's a lot of work that goes into getting that stuff. This is just sitting out. This is just testing. This is a thermocouple amplifier with 3 outputs. We can handle 3 thermocouples on one of our standard cables, and this was just making sure that the stuff I got back from the vendor matched the design specs, and that I actually knew what the design specs should be. And there was a learning process both on their side and our side. And we went through about 3, maybe 4 revs of these units before we were really, really happy that we were getting reliable thermocouple data under most all circumstances. And again, having that regularity on the sensor interfaces really made life a lot easier, because there were occasions where we had one of these units fail, and we're out live in the field. So what we would do is take the connector from these, repatch it on that panel while we're out there on the field, and keep the test day going. I could do a few quick changes on the display and repatch which one of those connections went to what on the screen as well. Debugging against reality is critical in doing these kinds of systems. You are fooling yourself if you think that you can sit on a bench with your software and hardware and, oh, it works fine. It worked fine in the lab. Those are famous last words. My consideration, until the software worked on the real hardware and worked with the real inputs coming in, it wasn't real. And one step further is that we gradually went from one version of the software to another during real test days. So I would come out with both versions preloaded. We would start off with the new version, do let's say a couple of simple tests out front. Then I would switch to the old software, analyze the new software's output back in the lab. Then the next test day out, we go another step, and probably about the third one, we would switch over to the new rev. So we had a very controlled, very careful process, and at each step of the way, well, when I got to the point where we decided this was ready to fly, or this was good, that version was frozen, it was given a part number, and nobody touched it. It existed as a thing. And then any further development was on a new rev that was entirely separate. And just so you know, any numbers that you happen to be able to read back there will tell our local espionage people absolutely nothing, because those are temperature and pressures at Mojave.
God help you if you try to change something.
Yeah, I got annoyed about it. Okay, one of the things that did turn up as an issue at one point, and this is the problems with real time, is that there are multiple ways in which you can get your data in on a real-time system, and I'll enumerate some of them later. I chose to do it by polled data, and the reason is I wanted to make sure that when I got a sample from all of the different things, that I got them at one particular time, and that I wasn't dealing with all the delays and the time coming through the system. The issue is that I had a 320 microsecond window to poll the data, read it back from the remote point, and get it onto my disk. And I had to do that millions of times without failure. Now, obviously, there are some stochastic issues here. you're going to lose a sample now and then. But we were way, way down in the, maybe 100% or less of samples dropped. And what those diagrams basically were is that I was having a problem with some dropouts, and I started checking the deltas between the times that we read and the times that the data came. And I found that our window was basically slipping. You would lose a sample. Your window of time of your 320 microseconds, if you're falling behind a little bit, it slides a little bit along, and finally it reaches the point where you miss the sample on that window from the hardware on the remote, and you slide over, and all of a sudden, bang, you've missed one and you're on the next sample. Now, we could tell that was happening because we had timestamps on every sample. So I could go back through those numbers very laboriously and see exactly where and what was going on. Okay, this sort of summarizes a lot of the things that I was saying. Now, there are different ways that you can do this kind of syncing. You can do what's called data push, which is the data is sent from the remote system. The problem with that is that the data is being rammed down your throat, and if you're not ready for it, you're screwed. You can do a ship-wide clock signal, which is done on some military systems. The problem with that is that you've now got a standard signal which has to snake its way all over the craft. Any place that you're going to have to need that, you're going to have to wire it in. You've got to worry about the time delays on that. You're going to have to, again, worry about the ground looping problems, a whole bunch of issues. Now, a question that was earlier, I ran this with up to 4 data acquisition systems. We had data rates coming in of, well, what was interesting is there is a difference between a latency and bandwidth. Now, intuitively you figure, I've got a gigabit ether link. But the time, what was mattered to us was the time it took for our block of data to get from one point to another. There were lots and lots of room for those little blocks of time in a million bits per second, or a billion bits per second. But it didn't matter, because if we didn't get that window of data from this unit to the little computer up here within its time slot, we still lost the data. But what it meant was we could have a whole bunch of different boxes, and they aren't really interfering with each other because they're in this vast ocean of possible time slots. And if any one of them can get its data back in time, all of them basically can. So we have a fair amount of expandability in the way that we do that. And that's where some of that hierarchy and tree came in useful. This was an issue which, well, Jeff is gone, but Randall probably, yeah.
I learned some new words from you.
And that's saying something coming from a Marine.
3 minutes.
Okay, I will move this up then. But needless to say, I spent a lot of time looking for why we were losing memory during operations. Now, the key to some of this was some days you have a really bad day in this industry. Now, you're familiar with those. That's one of my own photos, as is that. This was a bad day for mass and aerospace, and I managed to catch the impact. Okay, skip over there. We have a patent at Immortal Data on this distributed black box concept. The idea is, as I showed on the links, you have the memories spread around the vehicle. And what is different in what we have on our patent is that each one of those has its own GPS. So if this aircraft here gets blown up, this GPS and the data that they're getting, they're all sharing the data. You have all of it at one time, when this line gets cut, you've got the timing of when things broke. And since they've got GPSs, this wing falls this way and this cockpit falls off that way, you get the initial trajectory information until those wireless links are out of the way. You recover any one of those, and you can then backtrace the trajectories of the other major elements, and you can get the timing of how the thing came apart. This is an overall diagram of what Immortal Data is working on, and it's mainly, you've seen the elements before. Our ship store is the thing which stores all that data in a basically indestructible format. This is the ship's log data that was on the links.
1 minute.
Okay, and this is where we currently are at our office. All those units that I'm talking about, these are real hardware. This is the ship's log test bed back here. Okay, I will ship here into the future. Our plans are, we're not going for critical systems immediately for deep space. We will develop onto that as time goes on. We're looking at neural nets as a future. I'm already talking with people at putting neural networks on those nodes so that we can collect so that we can do the feedback control systems. And just like with the early system I showed you from 1981, you've got the data flowing up and down, and then you have the nodes with abstracted data.
Time's up.
Okay. And last slide. Okay. So we are at the absolute end of the time, or no questions?
No.
Okay.
Sorry.
Okay, well, you can always catch me around